All right, we're at section 14.6, Bernoulli's equation. Uh, there's going to be quite a bit of derivation, but we're going to end up with Bernoulli's equation, and you'll see that at the end. Okay, we're going to discuss the work done, the work of one, this this portion over here. The work of one is the force times the distance, F1 delta X1. Well, what is force one? That's the pressure times the area. So F1 delta X1 is equal to P1 A1 times delta X1, which is P1 V. A1 delta X1 is the volume. And we can see that the uh, work two is minus P2A2 delta X2 is equal to minus P2 times the volume. The same volume. We're um, we're discussing streamline flow and incompressible fluid, so the volume is the same. So the work is equal to P1 minus P2 times the volume. Uh, and so now if we consider the change in kinetic and potential energy, gravitational potential energy, we know that the kinetic energy plus the gravitational potential energy equals the work. And so for the kinetic energy, we have 1/2 mv squared plus the kinetic energy of the gray area, this area here, and this area here, minus 1/2 mv1 squared plus the k of the gray area. And we're going to assume that this k of the gray area is the same in both A and B. So we end up with 1/2 mv squared minus 1/2 mv, I'm sorry, 1/2 m v2 squared minus m 1/2 m v1 squared. I had to change the equation a little bit, so you're going to see my LaTeX script and not the script that you normally get. Now, if we consider the potential energy, gravitational potential energy, we're going to get mg y2 plus potential energy of the gray area minus mg y1 plus the potential energy of the gray area. And that, again, assuming that the potential energy of the gray area is the same, we're going to get mg y2 minus mg y1. Now, let's combine those two equations, and we have, I'm talking about the previous equation, this one, 1/2 mv2 squared minus 1/2 mv1 squared. If we combine that equation and this equation, we get 1/2 mv2 squared minus 1/2 mv1 squared plus mgy2 minus mgy1 equals P1 minus P2 times the volume. Now let's divide both sides by the volume, and remember that mass divided by the volume is equal to the density. We'll get this equation, 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho gy2 minus rho gy1 equals P1 minus P2. Now let's group all the ones together and all the twos together, and we get P1 plus 1/2 rho v1 squared plus rho gy1 equals P2 plus 1/2 v2 squared plus rho gy squared. And that gives us Bernoulli's equation, which says that Bernoulli's equation says that the pressure plus 1/2 rho v squared plus rho gy is equal to the constant. And uh, what does this say? Bernoulli equation shows that the pressure of the fluid decreases as the speed of the fluid increases. Um, you so the we'll see this application in an airfoil. If this when the speed uh, of the flow increases, the pressure decreases, and it also says that the pressure decreases as elevation increases. That's the bottom line of Bernoulli's equation. And for fluids at rest, there is no velocity, so P1 minus P2 equals rho g times y2 minus y1, which is equal to rho gh, which we've already seen. and that's for fluids at rest. So you observe two helium balloons floating next to each other at the ends of strings secured to a table. The facing surfaces of the balloons are separated by 1 to 2 centimeters. You blow through the small space between the balloons. What happens to the balloons? Well, you just imagine these balloons are separated by just a little bit. If you blow between them, what did we just discuss? Bernoulli's equation. So if you blow between them, you've got velocity here. The velocity increases. It was 0 before. The pressure between them decreases. So they're going to come together. So they move toward each other. Um, let's see, and that's it for Bernoulli's equation. Um, the We'll do some problems, and I encourage you to look at the examples, um, but we'll stop it here.